Welcome to day 2 of the 2022 Gravitational Wave Open Data Workshop. Today we've got 2 excellent speakers lined up, and I'm really looking forward to their talks. I think without further ado, we can jump straight into it. So our first speaker today is going to be Maya Fishbach. Maya is currently a NASA Hubble Fellow at Sierra at Northwestern University. And she's going to tell us today about the physics of compact object mergers. Maya, thank you so much for being with us today.
Yeah, thanks everyone for being here. Let me just share some slides. Sorry, I'm trying to also get it to be in the virtual room here. Okay. Okay, hopefully that is working for people on Zoom as well. Yeah, so I'll just get started. I'm going to give an introduction to some physics and astronomy that we can do with compact binary coalescences. And most of this talk will just be me explaining what a compact binary coalescence actually is. But before I do that, let's just look at this simulation that helps visualize what we're talking about with these compact binary coalescences, or CBCs. So here in this simulation, in this movie, you can see we have 2 compact objects, black holes in this case, that are in this binary system. So they're gravitationally bound to each other, and they're orbiting around each other in this in-spiral phase, and they're actually getting closer and closer together through the emission of gravitational radiation. So this gravitational radiation is carrying away that orbital energy and angular momentum until those 2 compact objects, in this case black holes, merge. And so these are the kinds of sources that we're talking about with these compact binary coalescences. We can't actually see this happening like you were able to see in this simulation, but we can detect that gravitational radiation, and from that observation of the gravitational waves, infer that this happened. Okay, so what are compact objects? So in the simulation that I just showed, you saw these 2 black holes. There's those black circles. Black holes are the densest objects. So they're so dense that not even light can escape this region outside black holes known as the event horizon. And so they're completely dark because they don't emit any light. A lot of you may be picturing this picture when you think of a black hole. This just came out from the EHT collaboration. This is actually a picture of the black hole in the center of our galaxy, Sagittarius A star. And here you can see this shadow of the black hole. So this light here that you can see is light that is very close to the black hole, but still outside of it, because this region at the center here is the black hole, which does not emit any light. This black hole is actually millions of times more massive than the black holes that we're observing with LIGO, Virgo, and Cagra. But it's, other than being much bigger, it's pretty much the same thing, just this very dense object. So the other kind of compact objects that we talk about and that we're observing are neutron stars. So neutron stars are slightly less dense than black hole. They're kind of as dense as an object can be before collapsing to a black hole. So they're still unimaginably dense, denser than anything we can imagine here on Earth, but they're not completely dark. They're still made up of stuff. And just like the name neutron star suggests, the stuff that they're made up of is mostly neutrons. So neutrons, just like we have in an atomic nucleus, you have neutrons and protons. In a neutron star, you just have a lot of neutrons that are smushed together into these very dense city-sized regions that have a mass of 1 to 2 times the mass of our sun. So here you can see a picture of a neutron star in the center of this supernova remnant. And I'll talk a bit more about what supernovas are as well. So we now know what black holes and neutron stars are. Let me try to this.
Maya, I'm sorry to interrupt.
Oh, yeah.
There's a weird bug of Zoom that things sort of cover up the slides. When you're looking at your screen, do you see like Zoom controls over top of the slide?
Yes, I am trying to hide them.
Yeah,
Okay.
I know it's a challenge.
Okay, that's better, right?
That is better. Yeah, there's still one. Well, I think that's a banner there it goes. Very good. Yep, much better. Thank you.
Okay. Yes. Okay, so those were just some examples of black holes and neutron stars. That's what we mean by compact objects. So either a black hole or a neutron star. And these black holes and neutron stars are made in our universe as the end states of stellar evolution. So when we're observing black holes and neutron stars, we're actually observing the stellar graveyard. And when the way this happens in this extremely simplified picture here is that you start off with a massive star. So you need to start off with a star that's around 10 times more massive than our own sun in order to end up as a neutron star or black hole. And then during that, okay, I'm sorry, I think whenever someone enters the waiting room, my meeting controls come back. Okay, sorry about that. I don't know how to make it stop. Maybe if I stop being host.
Yeah, we can try that. It'll temporarily take away your screen share, but then I'll give it back to you.
Okay.
Actually, I'll tell you what, can you stop your screen share and then I'll try to make this work. Here we go. Okay, so there go your permissions. And okay, you should be able to screen share now. Sorry for the trouble.
Okay, yeah, sorry everyone. I feel like this kind of stuff changes with new versions of Zoom all the time. So still figuring things out a couple years in. But anyway, so we have these black holes and neutron stars in our universe. We know that one way that our universe makes them is from massive stars. So massive stars are around 10 times more massive than our sun, up to hundreds of times as massive as our sun. When they evolve, they actually evolve pretty quickly, and they can have these pretty dramatic deaths. So often these massive stars, when they reach the end of their life, they explode as this supernova and then leave behind a neutron star or a black hole. This supernova explosion phase, sometimes it's not as dramatic. Sometimes the star kind of just directly collapses into a black hole. But that's the general idea, is that these neutron stars or black holes that we're observing are really members of this stellar graveyard. They're allowing us to study what happens to really massive stars in our universe. So that's kind of just a very quick introduction to what these compact objects or these neutron stars or black holes are. the way that we study them is through these gravitational waves, right? So what happens is that when these two compact objects in this binary system coalesce, similar to the simulation that I showed in my first slide, they're sourcing these loud gravitational waves. And these gravitational waves, you can see here, there's these ripples in the space-time. They're perturbations that travel out over space-time from this source and then travel for billions of years across the universe until they reach our detectors. So what this gravitational wave signal looks like, so the amplitude of the gravitational wave is how much stretching and squeezing you have, as you kind of may remember yesterday from Jenny's talk. And as you have this compact binary coalescence, you can think of it as being in these three phases. In the case where you have these two compact objects here, when they're fairly far apart, they're in the in-spiral phase, and so they're orbiting around each other, and you have this frequency of the gravitational wave, which is twice the orbital frequency. So that mostly depends on the masses of your two compact objects. It also depends a little bit on their spins as you get closer and closer during this in-spiral. But as these gravitational waves are carrying away this orbital energy and angular momentum, these two compact objects are getting closer together. So the orbital frequency is increasing. And so the gravitational wave frequency increases as well. And the gravitational waves also get louder and louder as the two compact objects get closer together. Eventually, your two compact objects get close enough together that they actually merge, and you see this spike in the gravitational wave amplitude. And then you end up with this final compact object. In the case where you have this black hole left over, it rings down with a characteristic signal here that depends on the mass and spin of your final black hole. And this final part of the gravitational wave signal is called the ring down. So I mentioned that during the in-spiral phase, you have the orbital frequency and the amplitude increasing as you sweep across time. So you can see that here in this gravitational wave cartoon on the bottom. You can also see it here in the time frequency representation, right? So this is the frequency of the gravitational wave signal as time goes on. And the brightness of these bins here is proportional to how much energy there is at each time and frequency. And so you can see that the gravitational wave signal starts off at early times pretty quiet at low frequencies, and then as it sweeps across time, we increase the frequency and the loudness of that gravitational wave signal. And that sounds like a chirp, which maybe you will be able to hear now. Okay, so hopefully you were able to hear that, but that's what this gravitational wave signal would sound like if you put these vibrations, these frequencies into the auditory band. Okay, so that is just an introduction to what are these gravitational waves from compact binary coalescences. The amazing thing is that we now have many of these actual detections of these compact binary coalescences in gravitational waves. And so that's what you can see here in this poster made by Sudarshan and Karan. And here, each one of these panels represents one of these gravitational wave detections from a compact binary coalescence. The vast majority of these are binary black holes, such as this very first detection here, but there are also a couple of binary neutron stars and even neutron star black holes, so a mixed merger between a neutron star and a black hole that are in this latest catalog that has around 90 events in it. Another way you can visualize these, so that just showed like the gravitational wave chirps essentially of all of those events. You can also visualize this in this animation made by Zohair Doctor of each one of these events. In this case, the ones up to the first half of the third observing run, right? Each one of these chirps corresponds to an actual compact binary. So two black holes or neutron stars, or a neutron star and a black hole in some cases, actually orbiting around each other and participating in this coalescence. So this is great because in addition to just knowing that these black holes and neutron stars exist and that they actually merge with each other, which is quite amazing to realize that that happens all the time in our universe, we can actually learn a lot about these systems and a lot about our universe as a whole. And so the first thing we do is, after we detect the gravitational waves, what you'll hear about in the next lecture, is what you'll hear about in the lecture after that tomorrow, which is to actually try to infer what are we seeing. So the gravitational waves are encoding some aspects of the properties of the sources. For example, how big they are. So this is to first order kind of the best thing that we can measure, because this is just setting the overall frequency of the gravitational wave signal, the masses of the two compact objects that are involved in the merger. We can also learn about how fast those compact objects are spinning. So are they spinning at all? Is their spin aligned with the orbital angular momentum, or are they spinning in the plane of the orbit? Then we can also learn about where did they merge. So that's one reason why it's really important for us to have multiple gravitational wave detectors in this network around the world, is that that allows us to localize the mergers better. And so we can actually try to pinpoint on the sky, where did this merger happen? And we can also measure the distance to this coalescence. And then another thing that we can measure in the case of neutron stars is how squishy they are. So the squishiness of neutron stars, because neutron stars are, again, actually made up of stuff, that stuff deforms in a particular way in a strong gravitational field. And those tides are encoded on the gravitational wave signal. And so we can try to understand exactly just how squishy these neutron stars are. So that allows us to measure these source properties for each event, the fact that those source properties are encoded in the gravitational wave signal. If you look at our catalog of gravitational wave events, then you'll get these plots and tables like this, which in this case are showing these one-dimensional posterior probability distributions on these various parameters. So for example, this first column here is showing the chirp mass of each of these sources that go across this way. And the width of each of these violins here is proportional to the posterior probability at that value. So in this case, for this first event that you see here, GW191103_012549, you can see that its chirp mass was most probably around 8 solar masses, and there's some probability that it was as high as, let's say, around 10 and as low as around 7. So that's what these posterior probabilities mean, and I think you'll encounter them a lot more in the tutorials and also in tomorrow's talks. In addition to learning about individual events, we can then combine this information across multiple events and learn things about the population of compact objects. So I think you'll also encounter this a bit in the tutorials. There are these population models that we then use to describe the distributions of these properties, like the masses and the spins, across multiple of these black hole and neutron star events. So one example of that is to fit a power law to the black hole mass distribution. So in this case, we might say that the merger rate of black hole mergers, it has this shape as a function of black hole mass, where there's quite a high rate at low masses, and then the rate declines with some power law slope up to the maximum black hole mass. So in this case, we use these masses that we've inferred for individual events and combine them all together to try to learn what is the minimum black hole mass in the universe, what is the slope of the power law function, what is the maximum black hole mass. So all of this together allows us to address many questions across physics and astronomy. So I'll just list some example of some questions that we're addressing right now. One thing is, how do the most massive stars live and die? And this is a very general question that we hope to understand about these massive stars in our universe. And we can get a handle on that by looking at things like the merger rate as a function of black hole mass that you can see here. So in plots like this is our inference of what is the merger rate at each black hole mass. These lines, these solid lines here is kind of the average over our uncertainty on what is the slope of the power law and things like that. And then there's these uncertainty intervals that you see here in blue, which are the 90% credibility intervals on what is the rate at each mass. And so you can see in blue is our latest inference on what is the merger rate as a function of black hole mass, compared to our previous to that inference, which is shown here in the black unfilled contours. And so when we measure something like this, we're learning, okay, what is the merger rate at each black hole mass? But that allows us to answer questions like, how small is the lightest black hole compared to the heaviest neutron star, which is telling us something about the supernova explosions that may give birth to these neutron stars and black holes. Another thing we can try to learn here is, okay, these most massive black holes, how many of them are there? And are they actually made from stellar collapse, or are they maybe made from mergers of smaller black holes, or some other way of making black holes? So another kind of question that we can answer is about neutron stars. So neutron stars are these very extreme laboratories for nuclear physics, essentially. And there's a lot that we don't know about them. So we don't actually know how dense are neutron stars. So how much mass can you put into a given radius for a neutron star? And so that's something that we can try to learn here by looking at how squishy these neutron stars are. So this is our inference from the first binary neutron star event, GW 170817, and we infer these tidal deformability parameters for each neutron star. If these are small, that means that the neutron stars are more compact, so they act more like black holes. You can see that we inferred that these neutron stars were actually quite compact and ruled out parts of parameter space with less compact neutron stars. Another thing that we can learn from neutron star collisions is how the heaviest elements in our universe are made. So in this movie here, you see this animation of two neutron stars merging. In addition to the gravitational waves that they emit really right before they merge, and that's how we're able to detect them in gravitational waves, they also emit this host of electromagnetic radiation. And it's very exciting. We can study kind of all of these many kinds of light that's emitted across the electromagnetic band together with the gravitational waves and try to piece together what happens when these neutron stars merge, because when that happens, you're essentially colliding to a lot of neutron-rich material together, and those neutrons interact with each other and actually synthesize some of the heaviest elements in our universe, like gold and platinum. And so that's something that's also very important to understand when we're trying to understand how chemistry is made in our universe. Another kind of question that we can answer from these gravitational wave observations is about the cosmology of our universe. So one question that we want to understand, because we live in this universe, is how old is it really? And one way to try to do that is to try to understand the expansion of the universe. So we know that the universe is like the surface of a balloon, where every point on the surface of the balloon is actually moving further away from the other points. So from our perspective, it looks like galaxies far away and objects far away at large distances are moving faster with this Hubble velocity. And we can try to measure what is the slope of this relationship. So how fast are objects at a given distance moving? And we can do that with gravitational wave observations in a really unique way, because gravitational waves are telling us the distance to the source that we observe. And if we have some other way of measuring the redshift or the Hubble velocity of that event, like we did in the case of that first binary neutron star event, because we could find its host galaxy and measure that redshift, then we can infer from having both the distance and the redshift what is the slope of this redshift distance relation, which is related to the Hubble parameter, which is then related to the constituents of our universe and also how old it is. So another kind of question that we can address has to do with the fundamental physics of gravity. So we observe these gravitational wave signals, and we can ask, do the gravitational wave signals that we observe actually look like what we expect them to from the theory of gravity, or that we have right now, which is called general relativity? And so there are many different ways that you can test, does this gravitational wave signal look like we expect it to? One example of that is by looking at the gravitational wave signal from each event and then splitting it into the low frequency part of the signal at the early in spiral, and then the high frequency part that has the merger and ring down, and trying to see whether the parameters that we infer for the source from the early frequency part is the same as the parameter that we infer from the high frequency part at the end of the merger. And so we can do that by looking at the final spin of that final black hole, and seeing whether the spin of the final black hole matches the spin that we would predict from the early part of the signal, and same for the mass of the final black hole, whether that matches the mass that we expect from the early part of the signal. And you can see that according to the theory that we analyze them in general relativity, we'd expect there to be no deviation. So we'd expect things to be around zero. And this is consistent with what we infer from analyzing the full population of events. And as we get more and more data, you can see here kind of moving from the dashed to the solid lines, we're getting a tighter and tighter constraint on the fact that general relativity seems to be really, really good as far as describing these events. Okay, so just to summarize this very brief introduction to hopefully what I've convinced you is a very rich scientific field. There's a lot we can learn from these compact binary coalescences. So first, I explained what these compact binary coalescences are, these black holes and neutron stars, which are these compact objects remnants of massive stars. When they coalesce, they source these loud gravitational waves, these ripples in space-time that we can observe in our detectors. The in spiral part of this gravitational wave signal sounds like a chirp that I played. And then this gravitational wave signal through its frequency and amplitude is carrying information about the source properties, like what is actually describing each individual system, the things like masses, spins, distance, and squishiness of neutron stars. And these detections are then able to teach us about many, many different things like massive stars, nuclear physics, cosmology, and gravity. So with that, I'll end my talk and take any questions.
Excellent.